So, in the last lecture we discussed about the Cauchy series, which has a component of mass matrix plus component of K matrix plus component of a combination of these. But the specific problem with the Cauchy series is that if you are including the third term, if you include the third term, then although K and M may be banded matrix, but still C will be a full matrix. So, this includes the computational timing. Is increased in this case, and therefore Rayleigh damping is preferred. With respect to Cauchy series, there is a third method by which we can do damping estimate. This is by damping matrix superpositioning. So, I will do the superpositioning of the damping matrix and try to find the C matrix for different modes. So, we already know that phi transpose C phi is C, where if you want to find damping at an nth degree of freedom or nth mode, we already know this is equal to zeta n of 2mn omega n for a classical damping. So, we know from this equation I can find C further as phi transpose inverse C phi inverse. Just do a mathematical manipulation here, pre multiply and post multiply, you can find C from this equation. Now, equation 3 will give you the C matrix completely, but since there are two matrix inversion is involved, this is again computationally complex. So, we can simplify this further. Let us see how. Remove this. So, for orthogonality, phi transpose m phi is a weighted mass matrix, we already know this. Therefore, pre multiplying and post multiplying I can find always phi transpose inverse as m phi m inverse and phi inverse as m inverse phi transpose. So, I call this as equation number 4. I can pre multiply and post multiply, I will get these two. So, what I wanted in equation 3 is a phi transpose inverse and the phi inverse, which are the modal matrix for the given problem. I have them here, and you may wonder that what is the advantage of doing it here with respect to doing it directly here. Now it is very simple here, because my mass matrix is diagonal. Okay. So phi transpose inverse with the mass matrix pre multiply post multiply inverse is simple compared to that of a overall inversion of a phi transpose matrix. Okay. So I can easily do these two steps here and find C. So let us substitute that here in equation 3. So substituting 4 in 3, I am just substituting phi transpose inverse and phi inverse here and get C. So if I do that, my C matrix now will become M phi M inverse of C of M inverse phi transpose M. Now since M and C are diagonal matrix, I can write C as like this, rewriting C can be, now instead of putting it as an inverse, I have n degrees of freedom, I want to do the summation for n degree, M, n varies from 1 to n, where n is the number of degrees of freedom, and substituting for C as 2 zeta omega m, I have got m square. So I can rewrite this slightly as 2 zeta n omega n by mn of phi transpose of n degree of freedom, and multiply this with m further. So the m here I have and the m here I have is what I have here and here, and C I said it is 2 zeta omega m, there is m square in the denominator, I got that m in here, 2 zeta omega n m. So I have everything with me here, I can easily find C matrix here for all the nth degree. So this is what I call damping superposition. I am superposing for every damping ratio for a respective frequency from nth degree. Okay. Now what are the critical advantages of this particular method? I call this equation number 5. So the critical observations, I am not saying advantages, critical observations of this method. See, even though there are n degrees of freedom in a given system, use only j where j is less than n, use only j degrees. Maybe you have got 10 degrees of freedom system problem, you are using only the first 3 degree. Okay. Even though you do that, the lack of using j plus 1th to nth modes, the remaining modes, you are using only j, I got n. So from j plus 1 till n, you are deleting that modes. Okay. So lack of using these modes will not cause numerical instability. That is advantage here. But there is a condition here. If you want to do this, then conditionally if the numerical integration of equation of motion is solved using unconditional stable time stepping procedure. So, if you are using this mathematical technique and delete the higher modes, it will not cause any numerical instability. Okay. So, the solution procedure is also advised by the literature. I will give you the references now in the presentation here. So, let us quickly do one problem to understand how do we do this application. So, you have got 3 methods by which you can compute C. One is simply, or rather 5 methods. One is simply you can take C as ratio of m, you can take C as ratio of k, you can take C as ratio of m and ratio of k, you can take C as ratio of m plus ratio of k plus higher ratio of this, and you can take C as summation of the modal superpositions. So, you have got different methods by which you can estimate C damping matrix. This is also a part of Rayleigh, both are Rayleigh. This is Cahe, this is Rayleigh, this is classical, all are classical damping. They have got different applicabilities. So, we cannot compare all of them. There is no question that I will get the same matrix by employing different techniques. Please remember this. These are not different methods of finding or comparing C. You will never get same C by all the methods, never. Okay. These are different procedures to get C. Most practically, Rayleigh damping is employed for offshore structures where FSI is involved, because the values which you get by damping of applying Rayleigh procedure is closely similar to what you get by experimental techniques in aerodynamic damping. That is what people have seen. Okay. There are references given in the literature, I will project it later in the second half of the lecture here today. So, there are references, people say that yes, let us use Rayleigh damping. That is why most probably you will see in most of the offshore structure problems people use Rayleigh damping. There is nothing like discourage, and many of them if you see intelligently have used modal superpositioning. Many papers would use this. Many of the land based structures, there is onshore structures problem will solve usually with this, usually. Okay. So, there are many varieties of applications and preferences given by the researchers for solving different kinds of problems. Before we solve and demonstrate an example problem on this, do you have any questions so far in the estimate of damping? So, we will move this, we will take up the same problem as we have been doing in the earlier examples, so that we can compare the C matrix clearly. So, I have a problem which is all are m, m and m. This is m1, m2, m3. So, m1, m2, m3 is m. This is k1, this is k2 and this is k3, which is k is 3000 kg and this is 1500 kilonewton per meter. So, for this we already know omega 1 is 11.8 radians per second and phi 1 was 1.68 and 0.32. Omega 2 is 29.27 radians per second and phi 2 was 1 minus 1 minus 1, and omega 3 is 44.778 radians per second and phi 3 was 1 minus 3.68 plus 4.68, single crossing, double crossing, zero crossing, first mode, second mode and third mode. Of course, we need M matrix for solving this. I need M, I have phi. Capital phi is nothing but the assembly of this matrix. I think we understand this. Okay. If you want to write capital phi for this problem, the first row will be the first column, the second row will be the second mode, third row will be the second. okay. I think this we understand. And M matrix for this problem, I will write it, okay, I will write it here. M matrix is M of 1 0 0 0 1 0 0 0 1. Off diagonal terms are not there in this problem. So what I wanted you to do is take zeta as 5%, I will remove this, I will retain this equation, take zeta as 5% and determine the damping matrix by superimposing the damping matrix of 5% for each mode. Take 5% for each mode, determine C, that is the damping matrix, by superimposing damping matrices. Of each mode. So let us do this problem. So let us compute C1 first, because I need to find the damping matrix in each mode. So let us do C1 first. So here n is 1, so this becomes m times of 2 zeta 1 omega 1 by m1 of phi 1 transpose of m1. So pre multiply post multiply zeta 5% and tell me what is C. Quick. So just for starting with the initiation, we can say like this: 2 times of 0.05 of 11.8 by 1, so of m phi 1 transpose. Yeah. So first pre multiply, then multiply, then post multiply, get the answer and get me C1. C1 will look like this. I will remove this. You work it out. So I will give you the C1 here. C1 is given by 10 power 6 of, so 3 by 3 matrix. (14.46, 9.83 and 4.63, 6.68, 3.15 and 1.48 symmetry. This is my C1. So now I want to get C2. Similarly, C2 substitute back here. So 2 into 0.05, that is what I am going to use. I should use 5% in each mode, that is my argument given here, into 29.27, that is my omega 2 of m phi transpose m. So pre multiply post multiply with phi and phi transposes and try to get C2, and C2 is 35.68 of 10 power 6 of, this is 35.86. One minus 1 minus 1 1 1 and 1 symmetry. So what I wanted, the C matrix is the summation of this for all modes. Okay, can also do for C3. So just say for example I have got C1 and C2, I won't take only 2 modes, as I already said. You need not have to take till n modes, you can always go to j modes, and j plus 1th to n will not cause any numerical instability to the problem. So any time you can truncate the modes what you want. So let us say I take C1 and C2. So, C matrix is sum of C1 and C2, I get C matrix. This is how I obtain the C matrix for this problem using by this method. Any doubt here? Any doubt here? So, if C3 is not present, what does it mean is the third mode does not contribute for damping, that is the meaning. Okay. Third mode is not contributing for damping. So, any doubt? You have to find the modal participation factor and weighted modes, that will come in the third module. What he is asking is a very intelligent question. How do I know where to truncate my number of modes? Practically and ideally speaking, you should take all the n number of modes, but in our problem we have 6 degrees of freedom, we may take all the 6. But you have got, let us say, infinite degrees of freedom in multi-story buildings, etc., very high large size dynamic problem. How do you truncate the modes? Truncation of modes depends on what is your modal participation factor coming onto the play. We will talk about that in the third module, then you will get an idea where to stop. Okay. So, now let us believe that ideally speaking I can include all the modes here. Kahi had this problem. When you talk about C or zeta, it was skipping at omega, omega 1, 3, 5, it was skipping in between some certain frequencies, is it not? But here you may not have to skip, you can continuously add all the damping ratios in all the modes and find the C matrix here. So, that is the, can say, as a different version of C matrix compared to Kahi. Of course, we understand Kahi series is an improvement on relay damping. Okay. So, relay damping is a fundamental model of reference what we have here. So, this has been practiced commonly and many of the international codes advise you to find C based on this. There are limitations, whether the modes are, whether the frequencies are widely spaced, whether they are closely spaced, there are many arguments. We will talk about all these things in the third module later. Okay. If I got omega 1, omega 2 very close to each other, how do you handle them? Okay. If I got all omegas successively by a difference of 0.01 radians per second, how do you handle them? So, we will talk about this later. So, now we understand that mathematically you can compute C till n degrees of freedom, anything you want, you can truncate. Literature says that if you truncate at j plus 1th onwards, there will be no numerical instability caused to the problem, that is what the literature says. Okay. So, this is an example application for the problem using this technique. Now, we have solved the same problem using 3 methods. You could also do it using the 4th and 5th method of C0, A0, M and A1 K, because you have M and K with you. You can always find all the 5 C matrices and could compare them and see how they are happening. One commonness between all of them is C will always remain as symmetric matrix. Okay. In this example, but not necessarily it will be symmetric, it depends upon the K and M matrices, right. So, in this example all were symmetric matrix, all were square, all were full sized matrix. Okay. It is not banded. Okay. So, computationally some are expensive, some are difficult. For example, this problem is computationally expensive because you have got to pre multiply and post multiply twice and do it, compared to Raleigh. Raleigh was simple because you simply know A1, A0 and A1, you simply multiply with M and K and get C. So, that was faster. So, there are advantages, disadvantages, how do they compare with the practical problems, etc. These are all given in the literature, we will not expose it much more than this in this. For your interest, you can refer more papers and understand how damping matrices are estimated for hydrodynamic involvement in offshore structures, etc. Okay. So, damping comes from essentially 2 sources, we have seen that. One is from the material degradation, other is from the geometric degradation. Okay. So, loss of stiffness is also compensation of energy loss, which is again a damping. Material degradation is also a damping source in general. In addition, in hydrodynamic we have got radiation damping, etc. We have discussed this in FSI in the previous lectures in the same module. Any questions? Move on to the presentation here. So, where we stopped was a TLP problem where we had a TLP where we derived the mass matrix, we derived the stiffness matrix, we now can derive the damping matrix. I will show you that now. So, let us quickly recollect what we have studied. The K matrix of the TLP which has been discussed is a square, non-symmetric, it has got very strong heave coupling with all degrees of freedom. Off diagonal probes present in the K matrix reflect the coupling of degrees of freedom with different other degrees of freedom. The coefficients of stiffness matrix depend on change in tether tension, so it is not constant, it varies with time. Therefore, K becomes response dependent of this problem, and coefficients of K of course are non-linear, we have seen them in detail, how are they non-linear. Therefore, K is not constant, but keeps on changing with respect to time while you solve the problem. Coming back to the mass matrix, structural mass is assumed to be lumped at every degree of freedom, therefore, the mass matrix is supposed to remain diagonal, but the off diagonal terms also present, they indicate the contribution of added mass term due to hydrodynamic loading. The loading is attracted in this problem only in 3 degrees of freedom, that is surge, heave and pitch degrees of freedom, because of unidirectional wave acting on the structure. So, coming to the damping matrix, the present study uses Rayleigh damping because it is more practical and applicable to TLP, because we have an advantage, TLP has got 2 distinct groups of degrees of freedom, one is stiff and one is flexible. I can easily select 2 ratios and do Rayleigh damping for this. So, this model applies Rayleigh damping. So, what we have used in this study is A0m and A1k, and of course, C will also get updated because K is getting updated. Okay. So, we will pick up an example problem which has been discussed in this particular paper in Taylor and Francis Ship and Offshore, but still we just present an excerpts of this paper directly. So, this is a very interesting problem. I will tell you what is this, why we have not taken a very conventional problem of solving a simple TLP with the regular wave, because that is available in many of the papers. I will show you a long reference later. There is a very interesting problem what we attempted through this particular study. Let us say in Gulf of Mexico at Mississippi Canyon Bay, in Gulf of Mexico at Mississippi Canyon Bay as a specific geographic location, we have got Mars TLP located, is located. So, there has been observations in this specific sea state that there is a distinctly high sea waves which come in this location. The wave height is very high. What does it mean is, if you look at the time history record of a wave, distinctly there is a shoot up and then it dies down. This kind of phenomena is noticed in this site by experimental measurements by Kim and Zhou. I will show you who are these literature references, I will show you later. Now, how to handle this kind of an exclusive impulse wave height in an analysis, because this has not been done so far, right. So, that is a very, the reason they have found out is, in this specific location, whenever there is a seabed movement in x and y direction, there is an excitation of this wave here. So, this study superimposes seismic excitation on a distinctly high sea wave and analyzes a TLP of this order. But you may wonder that why the paper analyzes TLP existing, because existing TLP is safe, Mars TLP is still functional. Okay. So, this paper does not study Mars TLP, this paper arrives an economic geometry from Mars TLP which is triangular in shape. So, there is a geometric optimization done on an existing TLP and checked whether that TLP is safe for this. Okay. So, it has got new innovative form derived from an existing TLP, and examining the TLP for a worst sea state which has been observed by the researchers practically, experimentally, for which this TLP has not been designed. You understand the point. So, the problem is completely different. Okay, it is not a conventional problem. So, I picked up this problem for demonstration because it is easy and it will be interesting for us to understand how does it vary or how it is different from. So, this problem analyzes DLP on a distinctly high sea waves in the presence of seismic excitation. The sea surface elevation of a high sea wave is a critical for a given sea state. The shape is steep and asymmetric, that is very important. I will show you the wave time history, it is asymmetric with respect to both the axes, horizontal and vertical, because this is what is referred as a distinctly high sea wave by Kreibel and Alsina. Okay. If the wave remains asymmetric and steep in shape in both the axes, then we call this as distinctly high C wave. The shape of these experimentally observed extreme waves are also available, and they should compare with the theoretical ones what are generating, because theoretically people have not generated this wave, but experimentally they have measured this wave. Zhou and Kim has done this, and if you generate a wave numerically for analytical investigations for this problem, this wave should match with that of what you have in the experimental observation. Okay. So, there is a limitation within which you must develop your model, update your generation of the loading first, then apply to the problem. Okay. The loading itself is updated with the experimental observation in this particular case. So, no systematic model was available for this kind of analysis, because people have not analyzed the Mars TLP for a seismic excitation, the Mars TLP for a distinctly high C waves which has been observed in the specific location by the experimental methods by different researchers. So, a new innovation was done by changing the shape to a different configuration in terms of its geometry, and then this analysis has been done. So, stability has been also verified in this problem. So, let us see how it is done quickly. So, in the present study we talk about distinctly high C waves which are generated through nonlinear kinematic wave theory. I am not talking about the generation of the wave, I will give you a very brief hint about it. The water particle kinematics has been obtained using Airy's wave theory with a randomly generated sea surface spectrum given by Pearson-Moskowitz. You can always modify the spectrum to obtain a specific nonlinear kinematic wave theory application using one parameter which has been given by Pilotto et al. Okay, Pilotto has said can modify this existing spectrum with one parameter variation which can fit for a nonlinear kinematic wave theory degeneration, which has been done in this problem. So, that is the equation we have, S eta eta omega, that is a spectrum which is having only one parameter which is omega variation. Omega m is taken as the modal frequency or specific mode. We have said it is 0.46 radians per second, there is a reason for this why, and S eta eta is of course the power spectral density function of the wave height, because I am worried about the wave height in this problem. Okay. So, once I do this, I generated a wave and picked up the sea surface elevation of the wave, because I want to plot the time history. Why I am plotting the time history, you may wonder, say when you have got a spectrum, from the spectrum directly we can do an analysis. Okay. You remember I am using a Rayleigh damping, the Rayleigh damping said I must use unconditional convergence, I must use a time stepping varying procedure. Okay. So, I want to convert this into time domain for two reasons, one is for this, and two, I want to be sure that the wave generated is steep and asymmetric. Okay. So, I must generate a wave of this specific order. Okay. So, the wave height on the preceding and succeeding is multi times larger than the convening wave height. This I can see only from the time history generation, and I also want to know at what time this is occurring or what frequency, is that frequency matching with my frequency or period of the structure. Okay, that is the reason. So, wave elevation is realized as a discrete sum, as you see here, of many sinusoidal functions given, and the functions are explained here. Ki is the wave number here, and omega I is the discrete sampling frequency where omega I minus 1, and n is the data points what you are considering for this, and phi is the random phase angle. The generated wave profile is designed to have a peak at a specific particular time t naught. So, I can fix this peak where I want to have. So, obviously I fixed up this peak at a specific degree of freedom of this TLP which can near resonate for a given loading. So, I can always check whether the TLP generated will be stable for this specific kind of a wave if it occurs. Okay. So, there is a freedom here that the T naught where I want to have this peak can be fixed by me in my analysis. Okay. I have picked up the T naught in this case to be as same as the period of heave. Okay. Let us see what happens here. So, this is a spectrum, sample history, you can see from the sample history the peak goes to 25 and the successive peaks are around 5, minus 5 and 10. Okay. And the highlighted wave shows a very specific window between 6 to 14 where this window is generated, highlighted. So, studies show that the generated wave should be continuous first of all and should have a concave front, then only it is accepted as an asymmetric wave. Okay. So, we have shown by blowing up the specific frequency or the window, time window, that is having a concave front is asymmetric, vertical and horizontal axis you can see from here, vertical and horizontal axis asymmetric, and it is having a specific T naught peak which is multi times larger than the successive peaks, what we call as distinctly high C waves. Okay. This has been completely, let us say, mapped with the time history measured by Zhou and Kim in 2000, and they were experimental values, this is analytical value. So, this is a TLP which is having a geometric form of triangular in shape. So, this has been derived exactly in the basis of Mars TLP which is 4-legged, which is square in shape. So, what is the basis for this comparison is given here. To arrive at an equivalent triangular geometry from that of a square geometry, there are two cases can be compared here by using a equation of static equilibrium for this problem. One, I say the buoyancy can be 4 T naught plus W, that is for square TLP, because T naught is tension in each leg, whereas for triangular TLP FB will be 3 T naught plus W, where W is the weight of the platform. So, by keeping the initial pre-tension same, T naught in triangular and square are kept same to the of square. So, what happens is 3 T0 will be much lower than 4 T0, so not 1.3 times lower than 4 T0. So, therefore, the total tension is reduced. This has been adjusted by increasing the weight. Okay. So, this is the basis on which the simple geometry has been evolved. So, without doing much alteration in the size of the TLP from that of square to a triangular which is existing, which is constructed already and functioning now, even now. So, a triangular geometry is attempted, and at that geometry now the periods are different. If you see here, these are the properties of 1, 2 and 3, these are 3 different TLPs which are available in the literature, which are existing TLPs. Okay. The literature says these are existing TLPs of square in shape. So, equivalent TLPs of triangular in shape has been arrived for TLP 1, TLP 2, TLP 3 based on the basis what we shown in the last slide. So, these are the natural periods and frequency in hertz, this is 1 by T, this is not radians per second. So, TLP 1 equivalent triangular, TLP 2 equivalent triangular, TLP 3 equivalent triangular, the periods are around varying from 80 to 130 in surge, whereas in heave it varies from 1 to 3 or 2 to 3 in pitch and heave, because they are stiff degrees of freedom. So, look at the frequencies in hertz for heave degree of freedom, it is about 0.5, 0.3 to 0.5, okay. But surge is very low, very large time period. Pitch and heave are relatively same, okay, stiff degrees. So, we have this geometric characteristics of this problem. Now, interestingly you see that the heave frequency what you see in this particular case is closer to the modal frequency of 0.46 what you have used in the PM spectrum. So, I am trying to look at the near resonance case in the stiff degree of platform and look whether the platform get completely uprooted in case of such waves coming and attacking the platform, because uprooting will happen only when the heave motion is phenomenally high. Okay. So, 0.46 is the modal frequency I have used in my PM spectrum, in the last slide we showed that, and 0.52 is my heave frequency. So, it is expected that a near resonance case can happen. In this case Rayleigh damping is used in the example problem. So, the force vector in your equation of motion which arise from a distinctly AC wave is computed using simple Morrison equation, because d by L of 0.2 is valid here. In addition, the dynamic teeter tension variation, as we discussed in one of the lectures in the same module, I am superimposing delta T values of the tether onto the superstructure and add that to my f of t in my problem. So, delta T what I get is from this equation, which is x of t minus xg of t, where x of t is my response function of my platform, where xg of t is having x1 of g and 3 of g, both horizontal and vertical motion of earthquake has been accounted for. Okay. Time histories both in surge axis as well as in heave axis has been accounted for in my xg of t. I am taking the relative motion now. So, this is my Kanai-Tajmi spectrum which we already wrote, we already have it, it is an artificially generated earthquake using KT power spectrum, the governing equation. There are 3 parameters of omega g, zeta g and s naught. Zeta g is the ground damping, okay, it is not the structural damping, and omega g is the ground frequency, and S naught of course the spectral ordinate for the specific problem which is available here. Okay. So they should be carefully selected to match a realistic earthquake. Now there has been an earthquake occurred in Gulf of Mexico on September 10, 2006 at 14:56 IST at a specific epicenter of 26.34 north and 86.57 west, where nearby 250 miles away in Florida, where in Gulf of Mexico a Mars TLP is located. So a specific spectrum of this specific M 5.8 Richter scale has been picked up with a ground acceleration of 0.25 g and 0.29 meter per second, and this has been used to generate a signal which is looking like this here. So this is my signal. So this is my power spectral density of the ground acceleration, which matches with exactly what we had in the specific geographic location occurred in the close vicinity of Mars TLP in Gulf of Mexico. The right side is the ground velocity time history. So this has been used because I need the ground velocity time history to compute my relative displacement in f of t, because of which my delta t will change in my tethers. Once delta t changes, of course k and m get updated, of course c also get updated. In addition, the buoyancy force changes and therefore f of t also changes. So I get the f of t right hand side vector as a sum of distinctly high C waves generated artificially using the modified Pearson Moscovitch spectrum plus delta t arising from artificially generated Kanai-Tajmi power spectrum in horizontal and vertical axis both. So I get superposition of both these forces. So equation of motion is solved in Newmark's integration scheme with alpha 0.25 and delta 0.5. So I have a detailed explanation for the Newmark's beta scheme, which we will discuss in tomorrow's lecture. We will work out an example and show how this can be done, but let us believe here that I know how to use a Newmark's beta integration scheme. So going ahead, the solution procedure, look at it here, will incorporate all the change in stiffness matrices of Kij, because this is going to be as a function of change in tether tension caused by seismic excitation. So my Kij will get updated in my solution procedure. Added mass will also get updated because of the variable submergence effect or the buoyancy effect. Set down and its effect will be also accounted for in the analysis, plus the hydrodynamic forces are instantly evaluated in the displaced portion of the platform. So all these non-linearities are accounted in my analysis, and the solution procedure takes care of this, and these are my results. The left hand side curves, this shows heave response in meters, this is pitch response in radians, and this is surge response in meters. You will see in more of these cases the heave response is more varying, whereas here there can be a specific order. Okay. Heave response is getting more exercised in this specific example because of 0.46 radians per second, 0.46 hertz, which is matching with the frequency of heave. If you look at the values of TLP 1, 2 and 3, what I wanted to show here is the tether tension variation. The tether tension variation is about 65% increased because of seismic excitation. So if you do not consider this, 65% increase in tension will not be accounted in the analysis. So this has happened because of presence of distinctly high sea waves and seismic excitation. So strain is about 0.29%. Okay, so it does not pull out on the tether, but the change in tension varies practically double or more or less at least 60%. So there is an increase. So we all understand that if change in tension increases by about 65 to 70%, think about K, M and omegas. So these are my power spectral density functions of the different responses in heave, pitch and surge. Of course you can see these responses in the paper in detail. So we will quickly look at the observations. Heave frequency response content is shows no visible damping, because you can see here this is not dying down, it is continuous. Okay, there is no question of dying down. Heave response is not dying down at all. So there is no visible damping present in the system, okay, which is contributing for decay of response. further, you will see that the heave response shows 3 peaks. One is closer to 0 and a very low magnitude which can be neglected. The other two are phenomenally high, which happens closer at the frequency of the heave degree of freedom itself. So, there is a resonance happening here, okay, which is quite dangerous. And the third peak is about 1.58 hertz. It is very interesting. This happens in pitch also. This happens in pitch also. You may see the value may be lower, it is happening in pitch. It happens in surge also, 1.58. What is this 1.58 number? The 1.58 number is interestingly is an average of the PM spectrum frequency and a Kanai-Tajmi spectrum frequency. It is happening in between these two. So, it is neither happening at Kanai-Tajmi spectrum frequency of earthquake or happening at loading frequency. It is happening an average of these two. If you look at the average, it becomes 1.58. So, this 1.58 is phenomenally seen in all degrees of freedom, heave, pitch and surge, and they are phenomenally high. Okay. Subsequently, to understand the stability, phase plots have been plotted for this specific problem to understand whether this is still stable. The phase plots becoming elliptical in nature, they show that they are stable with of course a long period. It is not circular, it is elliptical. So, quick conclusions from this study could be: the example problem illustrates a complete dynamic analysis of distinctly high sea waves in seismic excitation. You can see from this example that even stiff degree like heave is getting excited because of seismic force and distinctly high sea waves. A new geometric configuration has been attempted. The geometric form is derived from the equivalent square TLP existing in the site. So, there are many references for the whole lecture: nonlinear dynamic response Varavi, wave force on decks, Bhattacharya and Chandy coupled dynamics of T-star TLPs, Bhutan et al. Effect of tether damage, Kahe classical normal modes, my paper on dynamic behavior, my paper again on dynamic behavior of triangular TLP, influence of aerodynamic coefficients on ACE, ocean engineering, influence on triangular TLPs, then seismic analysis, then stability of tethers, Matthews stability, response behavior in Stokes nonlinear AACE paper, then impact loading, then dynamic Morrison equation, then distinctly AC waves, general and ship and offshore structures, then Chen on comparison of dynamic response, Kim et al. Dynamic response of TLP including hydrodynamic response, interaction of waves, Jeffrey and Patel model analysis, Bate and Wilson numerical methods in finite element analysis, Kobayashi dynamic response of TLPs in waves, Kurian et al. Parametric studies on TLP in random waves, Lau frequency domain analysis of TLP, Moe and Verley damping of offshore structures in current and waves, Morgan and Melieb dynamic analysis of TLP, Nordren analysis of high frequency vibration, Orio Nedzwicki knowledge based approach to design of TLPs, Roy and Craig structural dynamics introduction, Spanos and Agarwal response of TLP, Tobeshapur and Gulafasani comprehensive studies on TLP, Vanakuchi simplified optimal response, William et al. Motion tether prediction of TLPs, William Thomson theory of vibrations. So, I want that you should refer these papers to understand further. There are still okay. So, try to look at the literature of this and try to understand them, because what we have seen here in this lecture is, or in the couple of lectures, is how to estimate the damping K and M from the first principles, how a new geometric form can be attempted for a dynamic analysis, and how the equation motion can be solved using time stepping procedure, which we will discuss in the next lecture tomorrow using Nema's beta method. So, we will solve a problem and we will show you how this can be done, not for this case because it is iterative with 6 degrees of freedom. I will pick up a simple problem of 2 degrees of freedom and try to do the same procedure, so that at least convergence can be done in the class itself. So, this will help us to understand how I do dynamic analysis for a complaint structure like TLP. Okay.